Okay, so let's continue. What was I talking about? Right, so I tried to give you an introduction to why all this is important, and also what are the challenges. And now we want to take a step back and look at some of the fundamentals. So the first thing that is very important is thermodynamics. Thermodynamics is always important in life. The thermodynamics here basically say that the final state of a homogeneous system is governed by the classical law of thermodynamics, which means that we can look at first law, second law, and try to understand what they give us for understanding the combustion process. The things that we want to look at is, first of all, definitions here of thermodynamic quantities, and then we look at mass and energy balances, like what you do in thermodynamics. So these are a few of the things we want to look at. Elementary and global reactions, I just say a few words about this. Coupling function is a very important concept in combustion. We'll talk about this, stoichiometry, mixture fraction, and then Burke-Schumann solution. So basically, all of this is even before we really talk about energy, thermodynamics, energy. This is all just mass balances. So a few definitions here. Maybe I'll just go through this very quickly because you know all of this. Mole fraction is a quantity that we use to describe species composition in a mixture. The number of moles, basically 1 mole is 6 times 10 to the 23 molecules, is the Avogadro number, and basically mole is just a way of counting things. I could say we have so many mole of students here in the class, which is then something like 10 to the minus 22 mole. It's just counting, a way of counting molecules in a way that the numbers are more reasonable. So that's mole. We can define a partial. We can define a mole number of a species I, and if we add up all the mole numbers of all species, we get the total number of moles. We define the mole fraction as the number of moles for species I divided by the total mole number. Okay, so that's molecules of species I divided by total molecules in this room, and so that's one important quantity. Then we can also look at mass fraction. This was mole fraction. Mass fraction is the same in terms of mass. We define a partial mass here, which is Mi. Is the let's say in this room, it would be the mass of species nitrogen, for example, Mi, and that can be with a molecular weight. It can be converted. The mole number can be converted in the mass. And then if I define this partial mass, the sum of all partial mass gives you total mass, of course. And then we define the mass fraction as the mass of species I divided by the total mass. And the molecular weight that is used here to convert mole numbers in masses, the molecular weight can be determined if we know all the mole numbers, the mole fractions, or we know all the mass fractions with these formula here, and then I can also convert mole fraction into mass fraction. Okay, so all that is easy. Why do we need to define both? Why do we need to define mole numbers, mass, mole fraction, mass fraction? Why don't we just stick with one? It would make life so much easier if we would just use one and not, the whole range of things. The next slide will also, one of the next slides, we'll also define a concentration, which is yet different. It's basically the same thing. It's trying to see how much do I have of one species, compared to the rest. And why do we need all of these? No one? Guess?
Reactions happen on a molar basis, but masses will
Yeah, exactly. So the chemists love moles because if you write a chemical reaction, it's always based on the number of molecules that react with each other. So that's why we like moles. That's why we like concentration. We'll define this in a minute. But if you want to look at conservation properties, number of moles is not conserved. If you might have a reaction A plus B goes to C. That reaction will decrease the total number of moles. But the mass is conserved. So if we do balances, then mass is very good. So that's why we always need to switch back and forth between these two because we're interested in both aspects. There's another quantity that's very important, is the mass fraction of elements. That's very useful because, again, that is a quantity that's conserved. We know that if we have a certain mass fraction of carbon in our fuel air mixture, then after combustion, we'll have the same mass fraction of carbon. It will be in different species. The carbon first maybe is in the fuel. Later on, it's in the carbon dioxide, but we'll still have the same number. And so that's how that is defined. The mass fraction of J here means of an element mass fraction, and that comes from the mass fraction of a species, and then so this is the mass of that species divided by the molecular weight. That would be the mole number of that species times Aij. Here's a matrix that tells you how many of a certain element J do you have in species I. So for CH4, this would be 4 for hydrogen element and 1 for the carbon element. So that is just a matrix that you can write down very easily. That then tells you, multiplied by Aij, tells you how many, let's say, carbon atoms you have. And this is the weight of carbon or hydrogen or oxygen. And that then gives you the mass. And that sum over all species gives you. So this is just it's very, very simple relation to derive, but that gives you that element mass fraction. Again, the element mass, again, I can define an element mass fraction, which I can relate to the mass fraction of species, mole fraction of species, and so on. And of course, by definition, if I sum over all mole fractions, the sum of over all mole fractions must be equal to 1. Sum of all mass fractions must be equal to 1. Sum of all element mass fractions must be equal to 1. Okay? So then the next thing we define is what's called the partial molar density, or we call this typically the concentration. So all of these here, they are non-dimensional. Okay? The concentration is not non-dimensional. The concentration is the number of moles per unit volume. Why do we need to define this now also? Because chemical reaction rates, they are proportional to the concentration of individual species that participate in the reaction. Okay, so that's why this is very important. That's where we always use concentration. It's not non-dimensional. Units are mole by mole per cubic meter. Okay, and if we sum over all concentrations, this is how we write this in these brackets, or sometimes we just say CH4 means concentration of CH4. And if we sum over all these, we get the total concentration. So the total concentration, the sum of all concentrations of all species is not equal to 1. It's equal to the total concentration, total number of moles divided by the volume. Now, very often, people use the term concentration for mole fraction or for maybe for mass fraction, but mostly for mole fraction. Say the concentration of this species is whatever, 21%. That's not actually right. It's a little confusing, so try not to do that. Try to use concentration for this and mole fraction for the other. Okay? So that's something one should Usually, I'm not a big fan of being too strict on how we call things. You will see this, I also mess up terminology once in a while, as long as we know what we're talking about. But if I say concentration, I really mean mole fraction. That might be confusing to others. So sometimes it's good to stick to the actual terms. The density is defined like this. Partial density is defined like this. You know, we know all of this. This is an important relation. Our mass balances are usually in terms of mass fraction. So equations usually are in terms of mass fraction, but then in the equations for the mass fraction, you have chemical source term. Chemical source term is proportional to concentration, and this relation here tells you how to relate concentrations to mass fractions, okay? So the concentrations is density times the mass fraction divided by the molecular weight, okay? That's also an important relation, keep it in mind. Okay. So next thing here, ideal gas equation of state. We call this here, everyone knows this. There are 1,000 different forms of how to write this. I like, my preferred form is not even here, but P is nRT divided by V. That's one way to write it. We can write this also for the partial pressure. PI is then Ni times RT divided by volume. And I can, Ni divided by V here is concentration. You see this here, and the concentration I can write in terms of mass fraction. And the R is the universal gas constant, you know, which is just given. This is the thermally ideal, the equation of state for or the thermal equation of state for thermally ideal gases. There is this Dalton's law, which says that for ideal gases, the pressure is so small in the limit of ideal gas, the pressure is so small that two molecules in the gas are infinitely far apart, okay? So they fly around, but they never meet each other. They just, they never collide, okay? They're independent of each other. The only way how we see that there's more than one is if I'm the wall here, then once in a while, and a molecule here from the gas phase, a molecule will bounce off the wall or will hit the wall and bounce off, and that will give me, because it's a change in direction, it's a change in momentum of the molecule, that will act as a force on the wall, okay? And so if you take you know, all these impacts per area, that's a pressure, okay? So the you know, what we see then is the pressure that acts from these molecules. But it also says, because these species are infinitely far apart, I can superpose the impact of each individual molecule, or I could superpose the impact of each species in the gas mixture. So let's say I have here, this is nitrogen, and this is oxygen here in the room. Then I can treat these as if they were totally independent, because the nitrogen and oxygen molecules, they never collide anyways. So these two together give this, and then the impact they have in terms of pressure also is just the sum of the partial pressure of the individual species. Okay, so the total pressure is the sum of the partial pressures of the individual species, and the partial pressure, or it's this, and the partial pressure is just related to the number of moles at temperature and volume by this ideal gas equation of state. If I divide this here by this relation here, then you see that RT divided by the volume go away, and then, sorry, I go back and forth, and then PI divided by P is equal to Ni divided by Ns. Ni divided by Ns, that's the mole fraction, okay? So the mole fraction is equal to the partial pressure divided by the total pressure. is what this says. Okay, so that's an important relation. Also, it basically tells you that the ratio of partial pressures is the same as the ratio of mole fractions. Okay, mole fraction, volume fraction also, or no, we don't call it volume fraction, but mole fraction and partial pressure ratio are the same. Okay, for an ideal gas. So that's important. Also, each species always, there's no partial volume really. Each species always uses the entire volume, which is then related by this relation. Okay, so now with all this, you can convert here mole fraction or volume fraction. Here this says volume fraction. I just said there is no real volume fraction. I should change this. This would be partial pressure or whatever we call it. So anyway, so you can convert these into mass fraction, mole fraction, all of this. And so, by the way, in the lecture notes, you have all the slides. And some of these slides have this green caption. And I think usually it has this star also because I think maybe your handouts are black and white, so you can't really see if it's green or not. But so the star means this something is in the handout, and if you are not comfortable with either these concepts, you can look at an example here. But we won't cover this green stuff here in the lecture, just to save some time. Sometimes there are long derivations in the green stuff, and we don't do the derivations here. If you're excited about it, you can't sleep at night, just get your lecture notes. And why is that funny? Okay, good. So there's an example here, mass fractions, element mass fractions, and so on. Okay, chemical reactions, as I said, I won't talk about it much. We will talk, when we talk about premixed combustion, for example, we will talk about some chemistry. I'll tell you what is important for flames. We'll talk about the four-step mechanism. What are the most important reactions in flames and so on. But we don't say much about it. But we will talk about some chemistry. We will distinguish between elementary reactions and global reactions. That's a very important distinction. And that's why I'm mentioning this here. An elementary reaction, that's what Professor Pilling will talk about. This really describes a microprocess. You have a hydrogen radical, you have oxygen, and they literally collide with each other. Some activated complex will form. There's a lot of energy stuff going on. Potential energy surface, he will explain this to you, those of you who go in this course. And then, the molecule will break apart in a different way. Then here, for example, H plus O2 gives you OH plus O. And here, sometimes we use, in my class, we use combustion class at home, is not combustion scientists. We put a little circle here on the radicals so that the student, you guys know how to spot a radical. We use this for our students, but here sometimes we use these little circles here to denote the radical. It's not the reason why I'm saying this is not the common notation, that other people use. We just use this for our combustion class, make it a little easier for the students. So, these only take place with a collision, and you can determine reaction rates experimentally or theoretically using quantum chemical simulations and so on. Global reactions, on the other hand, they just give you the ratios of amounts of substances that react with each other. They give you stoichiometric relations, what the stoichiometry is. These are not microprocesses that happen. It's just an overall picture. Does not represent a microprocess, and there is no, you cannot compute a reaction rate for this. Maybe you can measure an overall rate at which this would happen at certain conditions, but it's not a theoretically well-defined process. So, but an example here is if you burn hydrogen, you need for each hydrogen molecule, you need one, for two hydrogen molecules, you need one oxygen molecule to convert this stoichiometrically to water. So this, I just mentioned elementary reactions. There's just a few more details here. It comes from a collision. Usually you don't have, in elementary reactions, usually you have maybe 1 or 2 molecules, maybe 3, but you don't have more than 3 molecules because it's very unlikely that more than 3 molecules at the same time crash into each other. Here we use, in this course, we usually use arrows to denote elementary reactions. They go in both ways. They go forward and reverse. And the forward and reverse, we'll see this later, the rates of these, they are related by thermodynamics. And the forward reverse, we often just use a double arrow or something. Global reactions just gives you basically conservation of elements, global ratios. They don't actually take place. And here we usually use an equal sign to denote this is a global reaction and not an elementary reaction. And it just means, you know, what I just said on the previous slide. Because it's not a real process, you can multiply the reaction, the stoichiometric coefficients in global reactions with any number. You can, for example, say 2H2 plus O2 go to H2O. You can also say hydrogen plus 1/2 O2 go to H2O, okay? There is no 1/2 O2, but because it's just stoichiometric ratios, it doesn't matter. You cannot do this for elementary reactions, of course. So you see they don't have real physical meaning in terms of actual reactions. So we use these here. If you multiply this then by molecular weights, then it also gives you the mass ratio of these species. Here, for example, 2 grams of hydrogen react with 16 grams of O2 to give you 18 grams of H2O. Okay, so that so this is just about the nomenclature or the symbols we use. We define stoichiometric coefficients of reactants and products, and the reactants we denote with a prime, products with prime prime. You see, if I do this for an elementary reaction, which really goes in both ways, it refers to what I wrote down, okay? I can write down A plus B goes to C for an elementary reaction, and I can say C goes to A plus B, okay? So the prime and prime prime really refers to what I wrote down. This here is the same for a global reaction. Here, for example, new prime here for methane is 1, and for hydrogen it's 2, okay? And then we also define this new without the primes. That is just the difference between the two, and that can be positive or negative. So this is negative for the reactants and positive for the products. So here, in this case, same thing. The new here is -1 now because this is consumed, and for the product, it's still 2. Okay, so again, these are different, and take note of this. So that's why we can write then here the equation, the rate of change of the concentration is equal to stoichiometric coefficient times reaction rate, and then this would be, if this is negative, then this will be consumed, and if it's positive, it will be produced. Okay, so that's what we do. So these can be positive or negative. The primes are always defined to be positive. Okay, just you know, just something to keep in mind. Global reactions, I don't need to tell you how to set up global reactions. I will tell you, you know, what's a global reaction for combustion of methane with oxygen. You just have to count what's left and right and make sure elements are conserved on the left and right side. Okay, and here's an example for how to do this. Now now we have all of this. This was basically just the notation that we use in this course. And the next point is coupling functions. So coupling functions, they're very important. They're essentially, they're a trivial concept. It's a very simple concept, but it's very important at the same time. So for example, I have a global reaction. 4H2 plus 2O2 gives 4H2O. And then, so 8 moles, I have 8 moles of hydrogen. And then the question is, how many moles of oxygen will have to be converted? It's a trivial, almost trivial question, okay? So how many? 4, okay. I just did an experiment. I wanted to see how bold a class this is. If I say it's a trivial question, usually nobody ever answers because, because the chances to be wrong are just too high. But okay, you guys are very bold. 4. So it's very easy. You see this immediately. How did you come up with that number? And the other question is, how many times the reaction has to take place? So if I want to convert 8 molecules of hydrogen, how many times does the reaction have to be executed? Okay, I have 8 molecules which I want to convert, molecules, right? How many times do I have to execute the reaction?
4 times.
If 4 times 4, that would be 16. Twice, right? So each time I execute the reaction, I use 4 molecules. I do it twice, I have 8 molecules. Okay, how do I come up with that number? I just divide the number I want to convert by the stoichiometric fraction. I can also do this in the equation. dci dt is the stoichiometric coefficient times the reaction rate. The global reaction, there's only one reaction rate here. The concentration is the mole number divided by the volume. And now I take this and I multiply this by volume. So on the left side here, then I have just Ni, and the volume appears here on the right side. And I divide it by the stoichiometric coefficient. Then on the left side, I have Ni divided by nu I, and on the right-hand side, I have omega times V. And the reason why I do this, the right-hand side is independent now of the species. That's the same for all species. I can write this equation here for oxygen, for hydrogen, and also for water. And it always gives me the same on the right-hand side. So for reaction, and that's the important point, Ni divided by nu I, or dNi by nu I, that is independent of the species. Okay, it's the same for all species. That's basically what we call the coupling function. So that change of Ni by nu I is the same for all species. So I can write this then more generally here. I have nu times fuel plus nu times oxidizer gives product. And then N1 divided by nu1 is the same as Ni divided by nu I, because it's the same for all species. And then I can write it like this. The change of Ni by nu I is the same as that of the fuel. Okay? I can, if I divide this here by the molecular weight of I, then I can write this in terms of mass. And then I divide this by density. I can also write it in terms of mass fraction. Okay? And now comes the beauty. I have this thing here. It relates the change of species I to the change of one species. Here I just take the fuel as an example. And I can integrate this over, let's say I have fuel-air mixture in a box, and I have it react up to a certain time. I can integrate this from 0, from the unburned state, to any given state. If I integrate it, I have here for the example of oxygen, I is oxygen now. I have Y oxygen minus Y oxygen in the beginning. That's the integral of this divided by this. And then this would be Y fuel divided by minus Y fuel in the beginning divided by this here for the fuel. Okay? So that's called a coupling function because it relates it couples the concentration of all species to the concentration of fuel. Or I could also couple to the concentration of oxygen. which means if I have a one-step global reaction, I don't need to solve equations for each single species. I only need one, okay? Because all others are coupled. And they're coupled because it's obvious. If I convert 1 mole of fuel, I convert a certain number of oxygen, okay? It's just what the global reaction tells me. So they're mathematically all coupled. So these coupling functions, they are very, very useful, especially when we assume one-step global chemistry, which is wrong because it's not the real life, but in analysis, we use it very often. In combustion theory, to try to understand things, we use it very often. So this is an example here. So I can write this. If I take this nu times m, these are quantities I know. I know the molecular. So you see here, let me go back. We use W as the molecular weight, but sometimes I use M. I haven't changed it everywhere, and sometimes I realize I mix the symbols up because some of this is just translated from our German. W stands for weight, okay, and in German you would say molecular mass, and so we use M. So bear with me. Sometimes these symbols are messed up. But it's easy enough to understand. The more complex symbols we don't mess up. So, so this here is just from the global reaction. I know this. I know the molecular weight of oxygen is 32. So all these numbers are known. If I bring this to the other side, then you see the change in oxygen is nu times the change of fuel. And this here I can just get from the global reaction. Okay. So an example here, let's say you have a closed system of hydrogen and oxygen, and we want to burn 1 kilogram of hydrogen. The question is how much air do we need to do that, okay? For stoichiometric combustion of oxygen. And we can just, from this relation here, the change in fuel times nu is the change in oxygen. And so B here, by the way, is fuel in German. Is B. Basically, there's no German word really for fuel. The German word we use is basically means burning substance is the word for fuel. Burning substance, so that's why the B. Okay. So there's some Germanisms here in my slides. Anyways, the nu here I just get from this. Here the nu is the stoichiometric coefficient times molecular weight. Stoichiometric coefficient is 1 times molecular weight. That gives you 8. So the delta M is 8 times that of the fuel. And then I have a lot of nitrogen also. This is the mass ratio of nitrogen to oxygen in air. So if I multiply it by this also, then you see if you want to burn 1 kilogram of hydrogen, you need 26 kilograms of air. Okay, so it's very easy to do this, but sometimes we don't appreciate these these ratios very much. Now, hydrogen is particularly bad, but also for hydrocarbon fuels. Usually, you need a lot more air, maybe 20 times, or maybe 15 to 20 times the amount of air the amount of fuel. So if you have a fuel-air ratio, there's always a very small fraction of mass fraction of fuel and a large mass fraction of air. Here's another one. How much CO2 is formed when we burn 1 liter of gasoline? Okay, simple question. We assume density of liquid gasoline is 0.75 kilogram per liter, and we approximate gasoline by isooctane. Isooctane is a surrogate that we often use to represent high-octane gasoline. Starting point here is a global reaction. It's easy to write it down. Isooctane plus 12.502 goes to CO2 and water. We use the same relation as earlier. Now we relate the fuel with the CO2. And then again, this here we can easily determine from the global reaction molecular weight of the species. And we find that When we convert 1 liter of gasoline, we produce 2.3 kilograms of CO2. So that is, under standard conditions, 1 cubic meter of CO2. Okay? So that's a lot of CO2. If you think of 1% of CO2, if you have a very clean cubic meter of air, no CO2, and you want to pollute it with just 1%, you see by burning one liter of gasoline, you would pollute on the order of 100 cubic meters of air. Okay, so that's a big number again. And every one of you uses 1.3 liter, we said in the beginning. So everyone, this is roughly the CO2 you produce every day. So, okay, so that's coupling functions. Coupling function, important concept. Stoichiometry, you know these things, but we'll just go through these quickly to establish the notation. When we talk about stoichiometry, we mean the fuel-air ratio that you have. Stoichiometric means the fuel-air ratio that you have to convert a hydrocarbon to CO2 and H2O. We can write the global reaction here like this. And then you can actually find the stoichiometric coefficients here for this. Then the mole number, so the stoichiometric mass ratio, we get this from, first of all, the mole numbers we have. So the mole number of oxygen divided by the mole number of fuel that you need for stoichiometric combustion. That's the same as the ratio of the stoichiometric coefficients in the global reaction, obvious. And we can divide this or convert this now to a mass ratio by multiplying here with the molecular weights. And turns out the molecular mass, the mass ratio, the stoichiometric mass ratio is exactly this coefficient nu that we had found earlier. Here, this nu O2, WO2 divided by nu F times WF. So that's the stoichiometric mass ratio that also appeared in the coupling function. That's an important quantity also. So typical values here, methane, nu is 4, dodecans 3.5. So you see for most hydrocarbons, it's on the order of 4, right? Roughly on the order of 4. Okay, so fuel and oxidizer are both consumed when combustion is complete if you burn these substances with the stoichiometric mass ratio. This again says consistent with the coupling function because this is exactly the coefficient that appeared there. If I write the coupling function like this in integrated form, and I set at the end when combustion is completed, then YF and YO2 should be 0, which means this here should be 0, which shows exactly the relation we had on the previous slide. So it's consistent with coupling function, is no surprise. There are other quantities like minimum or the minimum oxygen requirement and others, which appear here in the green stuff. If you want to look at this, this is the minimum air requirement and so on. We just want to introduce here the equivalence ratio. The equivalence ratio now is based on let's say, the stoichiometric mass ratio. Stoichiometric mass ratio, if I tell you it's 4, it doesn't tell you very much. If I say I have a mass ratio of 6, then it doesn't tell you very much. You have to think what's the fuel and all of this, which is why we define this quantity equivalence ratio, which is the mass ratio I have between fuel and air, fuel and oxygen, divided by the stoichiometric value. Okay, that's all it is. Okay, it's the mass ratio I have divided by the stoichiometric value. The stoichiometric value is just this nu factor, And so I can write it again with this stoichiometric mass ratio. So then, if this value is 1, I know it's exactly stoichiometric. If it's 2, I know I have twice the mass of oxygen of fuel I need. And if it's 0.5, I know I have exactly half I need. I can convert this also in terms of mole fraction. I can write this in terms of mole fractions also. It works for both mole fraction and mass fraction. Okay, but equivalence ratio everyone knows anyways. So mix, yes?
Why do in some books they refer it to as air to fuel ratio rather than fuel to air ratio?
Yeah, so the question is, sometimes people use air to fuel ratio rather than fuel to air ratio. Very simple, of course. The air to fuel ratio, which often denoted as lambda, is 1 divided by the equivalence ratio. And you can use this or that. Turns out, in Germany, the industry, combustion industry, uses air to fuel ratio. People don't use equivalence ratio in Germany. In other parts of the world, it's just has historic reasons. In other parts of the world, people use equivalence ratio, which is why here we use equivalence ratio. But maybe once in a while, you will see in my notes here, you will see lambda, which is 1 divided by equivalence ratio. Maybe not, because we try to get rid of all the lambdas, but in our course, we would define the lambda, yeah. But just historic reasons. And it's just to make things a little more confusing. So the mixture fraction, though, that is a very important quantity that we want to define. Is a very important quantity, especially for non-premix combustion. The mixture fraction tells you how much of the mass locally you have, how much of that mass comes from the fuel and how much comes from the oxidizer. So what we do here is we say we have 2 different streams. One is the fuel stream, one is the oxidizer stream. Now, sometimes you have oxygen in the fuel stream. Like I showed you earlier, I had one stream that was a mixture of fuel and oxygen and led to a very rich premix flame. And then I have a second stream, which is the air from the environment. So the mixture fraction really only tells you you have 2 streams, and you know how much mass locally comes from stream 1, how much mass comes from stream 2. That's what it tells you. But most of the time, let's say, we assume that one of these streams is the fuel and one of the streams is air, maybe. It could be anything else also. You could have exhaust gas recirculation, but that's what typically happens. Now, these streams, they mix and burn, and a nice thing about the mixture fraction, because it only looks at the mass, it doesn't care, so it's the same before and after combustion. So locally, so you could also look at it, it's very similar to the element mass fractions. The element mass fraction locally, I would say I have in the rich part, the carbon mass fraction would be high, in the lean part it would be low. And if I burn or not, that doesn't matter very much, because the carbon is carbon if it's in the fuel or if it's in the CO2. And similarly, the mixture fraction it just looks at where does the mass originate. Does it come from the fuel stream? Does it come from the oxidizer stream? So, so these 2 streams, they mix and burn, and as I said, often we have only one component in the fuel. Generally, it doesn't contain oxidizer, but it could. And the oxidizer stream, it generally doesn't contain fuel, but it could also contain fuel. I mean, again, it's just a mass ratio between 2 different streams. And then, so we define it. We usually call the fuel stream, we use subscript 1, oxidizer stream subscript 2. We define it as the mass that comes from stream 1 divided by the total mass. That's what it is locally. And the mass here means it could be, so M1, that would be the fuel stream. That could be the fuel, or it could be the carbon and the hydrogen in the water and the CO2 that originated from the fuel stream, okay? So this is defined, of course, you see this here between 0 and 1. In the oxidizer stream, the mixture fraction is 0. In the fuel stream, it's 1. Here, note index B means fuel, again. Mass fraction of fuel. In the fuel stream, we call this YB1, B for fuel, 1 for fuel stream. Oxygen in the oxidizer stream is YO22. And then we can look at the mixing before combustion. Then the mass of fuel is just the mass of fuel in the unburned is just the mass of fuel in stream 1 times the mass that locally originates from stream 1. And then we can write this. So if I divide this then by the total mass, I divide this by the total mass, then this here would be this mass fraction. And this is M1 divided by the total mass is a mixture fraction. And similarly, I can write this for the oxygen, and I get this. And then we have the coupling function from earlier. If I introduce here for these quantities, I introduce this and this, then I can here solve this for mixture fraction, and it gives me a definition here of mixture fraction. And you see in the fuel, so this has here a mass fraction of fuel, mass fraction of oxygen, and it has the oxygen mass fraction in the oxidizer stream and the fuel mass fraction in the fuel stream. And you see for if in the fuel stream YO2 is 0, let's say, and this is YB comma 1, and you see then this fraction is 1. And in the oxidizer stream, this here is 0, and then I have minus YO2 plus YO2, and it's 0, okay? So it's normalized between 0 and 1. And it seems like it depends on the combustion process itself, but you see that this nu times nu YB minus YO2, that's exactly the coupling function. It's exactly how these two are coupled together, which is why this becomes independent of the combustion process itself. So this was again the definition. And then for stoichiometric combustion, YB and YO2 have to disappear. So this here, and you see they do because this is again the stoichiometric mass ratio. So the stoichiometric value of mixture fraction comes from the definition where these two are 0. So this stoichiometric here would be YO22 divided by this denominator. And I can write it like this or like this, in a sense, this just gives you the local equivalence ratio, but in different values. This is shown here on the next slide. No, it's not shown on the next slide. This is shown in a minute. Yeah. So let's wait until that comes. But this now, this assumes that basically it assumes one-step global reaction because it just considers oxygen and fuel, no intermediate species. There's a different definition of this. Here's by Bob Bigger, and this is based on the elements, the element mass fractions. So if I have a global reaction like this, then I can, from we looked at earlier, from the coupling function here of the species, I can define coupling function of elements. Okay, so I have here the number of carbon divided now by nu F and the number of carbon in the fuel, D and H, by the number of hydrogen in the fuel and nu F. And again, these ratios, they're the same for all elements, okay? For the same reason we looked at before, only that now this is for elements, and these coefficients M and N appear here these values. So I can, if I divide this here, so these are the moles, change of numbers of carbon, hydrogen, oxygen. If I divide this by the weight of a carbon atom, hydrogen atom, then I can write this in terms of element mass fractions. And then I can define a coupling function here, which is carbon. So this change, plus this change, minus twice this change, that should then be a coupling function. And that should not change then by chemical reactions, because it's defined according to the coupling function. So that beta here is my coupling function. I can now normalize this. I want to normalize the beta so that it is 0 in stream 2, and it's 1 in stream 1. So I just define it, the mixture fraction is beta minus beta 2 divided by beta 1 minus beta 2. And you see now if in stream 2 this is equal to 0, and in stream 1 it will be equal to 1. And if I plug all this in, you see this is what I get. And now you can do measurements, maybe in a flame. You measure all species at one point, and you can see then locally what is the carbon, the carbon element mass fraction, hydrogen element mass fraction, oxygen element mass fraction, and then you can evaluate this quantity at each point. It's not easy to do this from experiments. You see this, but that would be something that I could relate to element mass fractions. So, because the elements are conserved during combustion, elements don't change. We said this earlier, which shows then also that this here mixture fraction defined like this does not change during combustion. If the mixing field, it only changed because of mixing and diffusion, not because of chemical reactions. So these are two different definitions of mixture fraction. We typically use the first one because, again, it's simple. If we use one-step global chemistry, we have only fuel and oxygen, and it's easy then to define these quantities. So this here shows how to relate the mixture fraction to the equivalence ratio. So the equivalence ratio is defined like this. If I introduce these functions here into this, then I rewrite this a little bit. I get this, and then you see here on this side, this is the equivalence ratio. So I can relate this to equivalence ratio such that the equivalence ratio depends here, or can be expressed from mixture fraction and the stoichiometric value of mixture fraction. So what this shows, first of all, is how to convert these two, but it also shows that the equivalence ratio is nothing else really than mixture fraction, or mixture fraction is nothing else than equivalence ratio. And then the question again is, why do we need to define mixture fraction at all if it's the same as equivalence ratio? What do you think? Why do we? So in combustion always, we express the same thing by 5 different quantities, which makes life complicated, but usually there's a reason for this also. What's the problem with equivalence ratio? Sorry? No, the equivalence ratio you can define locally. You can locally, if you know all the mass fractions, you can define it locally also. This gives one-to-one relation, yes, but what's the real problem with it? Sorry?
Normalized 0 to 1.
Yeah, it's not normalized between 0 and 1, right? For in air, it goes to, no, for oxygen, in pure fuel, it goes to infinity. So if I want to write an equation to solve the local equivalence ratio, that's an issue because it goes to infinity. So you can think of the mixture fraction as nothing else than just normalize the equivalence ratio such that it varies between 0 and 1. Then I can write a nice equation, and I can solve this equation without any singularities. why don't we only use mixer fraction? Because a mixer fraction of 0.15 doesn't tell you very much. For me, I know exactly what 0.15 means for different fuels, but if you're not used to this quantity that much, then it's hard. Equivalence ratio 1, 1.5, 0.5 is very easy to understand. Okay, so that's why. And you're right, the equivalence ratio, usually we use it as a global quantity, not as a local quantity, but equivalence ratio also you can define locally, and you see this here. Okay, so let's see where we are. We started 2 minutes late, so maybe we'll just finish this up. The equivalence ratio can also be formulated for multi-component fuels. Here is shown in this exercise. And it shows that, well, again, I just said this. It's the same as equivalence ratio. Okay, so maybe we stop here, and then we talk about the so-called Burke-Schumann solution as function of mixer fraction in the next lecture. So 15 minutes.